My name is James Ide. I'm one of the co-founders of Expo, and today I'd love to share with you an idea that we call linked literate programming, or LLP for short, and show how it helped implement parts of the web spec in a native mobile app. Let's start with a question. When agents write the code for us, where does our intent live? This question matters because a lot of the important work happens outside of our code. Today, agents can generate a lot of code. That's useful, but it also amplifies a very practical problem. We make decisions during a project. We discover constraints. We decide not to build certain things, and we learn why one approach works better than another. A lot of these choices and findings, they live in an agent chat session, and then they're just lost. These days, agent harnesses like Claude Code and Codex, they now have memory, and that's useful, but that memory tends to be tightly coupled to each harness, and there's a high amount of lock-in. In contrast, plain files, just like Markdown, they have zero lock-in. They're visible to us, they're very familiar. We commit Markdown files to a repo, and we can share them with our teammates. Linked literate programming uses plain files, mostly Markdown, to document our intent and provide memory across chat sessions with agents and between our human teammates. Foremost, linked literate programming is just an idea with two parts. We write specifications, and we link code back to those specifications so that the code and the specs stay in sync. These links are just plain code comments. They point to a precise section of a spec, or, when relevant, the entire spec document. And one of these linking comments, it's just the string @ref LLP followed by the name of the spec file and section. It's extremely lightweight and plain. Charlie Cheever, my co-founder and the CEO of Expo, has been exploring this idea in his own projects, especially projects where he doesn't need to read every single line of code, and he's looking at specs instead. He has a public repo called LLP on GitHub that explains the specifics and also includes helper agent skills. The links in linked literate programming give us a few benefits. The first is coverage. We can ask whether each part of our spec has at least one place in the code that references it. Is our spec fully implemented? The second is accuracy. We can go the other direction and ask an agent whether each piece of code actually and correctly implements the part of the spec that it references. Is our code in sync with our spec? And the third is intent. Code is meant to be modified over time. However, specs often cover broader decisions that the code doesn't fully capture at this exact moment. And so when an agent works on an existing piece of code, LLP guides the agent to also read in the linked spec. LLP helps agents consider both the implementation and the interface. So to demonstrate LLP for this talk, I wanted to use specs that were already written and had a lot of care and design behind them. This brings us to the web specs. LLP needs a spec, and writing a good spec takes work. The web specs are especially good. The authors have put a lot of thought into these APIs, the use cases, the edge cases, performance, documenting life cycles, interoperability with other web APIs. They have precise language that is useful when we're asking an agent to implement something faithfully. And so with web specs as the input, I wanted to see how far an agent could get using LLP. This here is the W3C camera API running in a native app on a real iPhone. It can switch between the front and rear cameras. It can change resolution, frame rate. This was built entirely using LLP. Agents imported the web camera spec into Markdown docs and then used LLP's linking comments in the generated code. And this whole native app was made with Expo. Expo is an open source React Native framework for making universal apps that run across Android, iOS, web, and other platforms as well, like TV. One pattern for universal apps that we found that works well often is to target the web APIs across all these platforms. On web, this means that the implementation of the API is 0. It's just there. It's built into the browser, and there's no library code to bundle or serve. And on native, we use Expo's native module system to implement web APIs using native code and the OS and device's native capabilities. The goal here is to create a common API across all platforms that then lets us share application code on top. And the web camera spec is a great stress test for a common API. I chose camera because it's very mobile first. On phones, the camera is a first-class device. We have front cameras, multiple rear cameras, different zoom levels, wide angle, telephoto, and on some devices, even depth hardware like LiDAR. And because the phone camera is more feature-rich than a typical laptop camera, this felt like a good stress test to implement a web spec on native. In a new repo, before coding anything, I asked my agent to set up LLP. Then I had it fetch the W3C camera spec and extract just the parts relevant to implementing camera on iPhone. The agent's main prompt used the new /goal command that they now support to ensure that every section of the W3C spec was referenced at least once in the code. And I also had the agent get an existing test suite for the camera APIs called the Web Platform Tests, or WPT for short. One interesting detail is that the agent initially only had access to an iOS simulator on my computer, as opposed to a physical iPhone. And the simulator doesn't have camera support by default. So the agent couldn't run tests that relied on a camera. And instead, the agent had to rely very heavily on the web specs, the code that the agent wrote, and static analysis to make sure that it implemented the web spec correctly. And this was one of the more striking parts of this project to me, because the initial camera demo actually just worked on my phone after only a few prompts. It wasn't quite one-shotting, but it was 3 or 4-shotting. And it didn't have a complete feedback loop for the agent at first. So making that feedback loop later on was important to get the test suite passing. The test harness with a few prompts, it now captures all errors that run in the app, and it sends them from the phone to the Expo dev server to be readable by the agent. And eventually, the agent got the full test suite passing, even on a physical iPhone. 246 out of 246 tests were passing. So with this foundation working, I started looking for existing browser demos that showed off the web camera API. I'd like to show this demo over here, where, whoops. This is WebGPU running the web camera that we implemented using the agent, and it's taking this camera feed, say hi to the camera, and, and projecting it onto a cube. It's running in this native app. I mentioned WebGPU, and bringing web APIs to React Native is not new. We've been doing this for years, actually, and a developer named William Candelon brought WebGPU to React Native using Dawn, which is a WebGPU implementation from Google. But now with agents, web specs, and LLP, all this work becomes more systematic. We also have demos that go beyond visual effects. For instance, we can do edge detection of the conference hall, show a kaleidoscope, which is fun. And GPUs, as we know, are not just for demonstrating visual effects, but they can also do AI analysis. Here's an app that runs a neural network to detect what it's seeing. It says, this is a laptop. I flip the camera around. Good, I am a human, I'm not a bot. And we can go even further. I mentioned that my iPhone has LiDAR depth hardware. And the web camera spec doesn't support depth sensing capabilities. However, the WebXR spec used for mixed reality does. And so using the same LP technique, I had the agent implement a subset of WebXR, and this is a depth sensing version of the camera app. The warmer colored contents, this is the laptop here and the little podium, they're colored more warmly, and items further away are colored in dark blue. And remember, the original point of this, or implementing web APIs, was for these demos to run on web. So the LiDAR demo does not run on web, but these other edge detection demos that rely on the camera API run in Chrome on my desktop here. One final finding is that making these demos took triple the time and tokens compared to implementing the W3C specs. This was very surprising to me. And when I thought about it some more, it's because the demos weren't as precisely specified as the camera API or the WebXR API. And so building these demos, they were greatly sped up with hot reloading in the Expo because it runs JavaScript in a native app. And for the token costs, I am sure glad I had a Claude subscription and a Codex trial. So thank you, OpenAI. This is not a formal eval in any case. It's just what happened in this project. And it shows that the work that had a detailed spec was a lot faster and cheaper. So everyone, I invite you to give LP a try in a project where you have specs. Ideally ones that precisely document your intent. That could be a technical spec or a product spec. Linked literal programming is foremost just an idea, and the LP repo on GitHub is just a way for you to start. The code for today's demo is also fully open source. And if using JavaScript to build both websites and native mobile apps sounds interesting to you, the Expo framework is free and open source. And come by our Expo booth at the conference today and say hi. Thank you again for spending these 10 minutes with me. I'm James Ide, and you've been a great audience, CascadiaJS. Thank you.